All right, so here's the good news, bad news over the next couple of days. The good news is that you don't have any homework for tonight or over the weekend, but the bad news is I have to try and entertain you and regale you with stories of velocity and position and vectors. That'll be the best I can. Okay, what?
It's not bad news, it's physics. We're prepared for it.
I know, but yes.
Mentally prepared.
We knew we signed up for the class.
I generally like to get you up and doing stuff, but you kind of have to lay this groundwork first. All right, so if you look at where we're at right now, and by the way, glancing at the tests, they look pretty good. I'll get those back to you tomorrow, so don't sweat that. So basically, right now, you have what you need to do physics. You know that we're measuring in kilograms meters per second. You know that acceleration is in meters per second squared. You know how to graph things. You know how to write significant figures. You know how to put units on there. You can now do physics. Okay, you have the skills that you need to do physics. Woo! Yes. Okay. Now, so the next 3 units are very sequential. So the first unit that we're going to have is velocity, and then from that we're going to have acceleration, and from that acceleration we're going to have force. Now, velocity, the short version is how fast you're going and in which direction you're moving. If you're going to change that, either how fast you're going or which direction you're moving, you're going to accelerate. So acceleration, the next unit, is going to be the rate of change in your velocity. So you have to understand what velocity is before you can begin to measure its rate of change, which is acceleration. Now, the third unit is going to be force. Short version of force is that it's force equals mass times acceleration. So you have to be able to do acceleration. So here's the sequence. You have to understand velocity, because to understand velocity, you understand acceleration. If you don't understand acceleration, then you don't understand forces. So we have to lay a very solid groundwork on this idea of velocity. Okay, so that's why I'm taking great pains to say, okay, when we talk about velocity, this is what we're talking about. Okay, so that's why this is going to take a kind of a day and a half to kind of get through this whole basis. Once you get that, then you have a very, very solid foundation, and we can build from that. Okay, now, let's say that you want to talk about velocity. Now, here's the short version of velocity. It is the rate of change in position. But when you're talking about position, that isn't as simple as it may seem. So if I said, Courtney, okay, where are you at in this room? By the door. Okay, now, take the camera, kind of pan around so they can kind of see what we're talking about with the door, and kind of pan that around. Okay? All right? And then bring that back over. All right? So, Courtney has just said that she's by the door. Okay? Now, might you think that's a little bit vague? Because my desk is by the door. The broom is by the door. Is there a way that you could maybe narrow that down a little bit?
I'm sitting by Abby Evans.
Okay, you're sitting by Abby Evans, who's also by the door, who's actually a little bit closer to the door. Now, sitting by Abby Evans. Well, she is the benchmark for everything is judged. So, there you go. Okay, so, okay, let's let the door be what we call the reference point. Okay, so there's any number of ways you could describe this. Let's say that Mr. Botts walks in, and he needs to specifically find you. How could you tell Mr. Botts specifically where you are in the room relative to the door? Like, say, for example, you would take so many steps.
I am about 2-3 meters straight heading to the door.
Okay, so if you walked in the door and walked straight, maybe 3 meters, you would be there. Okay, now I can live with that. Now, here's what Courtney did without knowing what Courtney did. Okay? Courtney defined the door as the reference point. Okay? So she is defining her position as relative to that reference point, which is the door. Now, walking straight is a little bit vague. Okay? So let's maybe say, in terms of directions, you could walk north. So if you say, okay, Mr. Boss, you walk in the door, you walk 3 meters straight north, boom, there I am. Okay? Now, let Abby Evans be the reference point, as well she should. Okay? So if I said, where are you in terms of the reference point of Abby Evans, what would you say?
I am north of Abby Evans, about 2
2 feet?
It's about 2 feet. I don't know.
How about a half a meter?
Half a meter, yeah.
Half a meter. Okay? Now,
We don't talk.
you have not changed, right? Your position has not changed. But if you're a half meter north of Abby versus 2 meters north of the door, or 3 meters, you're changing your description based upon a different reference point. Okay? Now, this room is what we're defining as our frame of reference. Okay, so we're defining everything that's going to happen within this room. So Courtney is saying within this room, I have a certain position relative to the door, relative to Abby. She could have said, my position is relative to my M&M coffee mug. Okay? What you pick as the reference point is completely arbitrary. Okay? There's no magic way to say, oh, this is what you always want the reference point to be. It's completely arbitrary. So let's say, for example, I take my little molecule, right, and I throw it up in the air. So here's the deal. If I make my hand the reference point, then I would say, well, it goes away from the reference point and then it comes back towards the reference point. If I make the ceiling the reference point, then it would be going towards the reference point and then back away from the reference point. So what you pick literally does not matter. It's arbitrary on how you do this. Now, Courtney, what is your velocity right now within this room? Why? Bingo. Now, you need to talk about something that's known as, and this is all about vocabulary. Displacement. Okay? The short version of displacement is that it's your position final minus your position initial. Okay? It's a short version of displacement. Now, if you look at what Courtney said, her final position right now is 3 meters north of the door. Her initial position was 3 meters north of the door, right? So when I take 3 meters minus 3 meters, check my math, I get 0. So she has no displacement. Okay, that's it. She has no displacement. So velocity is your displacement divided by time. So right now, she has no displacement. Divide that by however much time you want, 20 minutes, whatever. You got nothing. So she has a velocity that is 0. Now, Abby goes, well, or Courtney goes, well, I need to go to the bathroom. So Courtney's going to get up and she's going to start, so here's the room, okay? So she's going to start here, right? But we'll even color code this. Right there by Abby Evans with the blue hair, okay? Like that color? Yeah, it's a good look. Okay? We'll shade it a little bit. You got some black in there. Okay, cool. All right. So, that's not bad, actually. Look how it matches up. All right. So, she's right here beside Abby Evans. She's going to walk to the back of the room. So, her initial position, X naught, would be 3 meters. She walks to 6 meters. So, what's her displacement? Don't make this difficult. 3 meters. If I take 6 minus 3, I get 3. That's her displacement. Now, the variable here would be time to determine her velocity. She might stroll, kind of saunter, okay, right? Do this. She might quickly go, oh, the room's on fire. Oh, I'm going to run, okay? So, the only variable is going to be the time. So clearly, if she moves 3 meters in less time, what happens to her velocity? It goes up. So velocity, at its core, is the rate of change in your position. If your position is changing very slowly as a function of time, your velocity isn't very fast. If you're driving a Formula One race car at 200 miles per hour, your rate of change in your position is very rapid, and you have a very large velocity. Okay? So, when you talk about velocity and displacement, and this is on your lecture notes, velocity, acceleration, displacement are all what's known as vector quantities. Now, here's the short version of vector quantities. Vector quantity means it basically has two aspects to it. It has a magnitude, and don't flip out and go, oh, magnitude, that's a big word. Okay, magnitude is a fancy word for a number. Okay, magnitude just means number. That's it. Okay, so the displacement for Courtney would be 3 meters. If she walked all the way to, the Canadian border, her displacement would be much bigger. Okay, that's the magnitude. Now, so if it's a vector quantity, it has magnitude, so it has a number, and it has a particular direction. So in this case, I could draw that as what we call a vector, which is a fancy name for an arrow. So basically, if it makes sense to represent something that you can draw on a paper as an arrow, going here's the magnitude, okay, which is the length of the arrow, and you point that arrow in a particular direction, hey, it's a vector quantity. Now, let me give you an example of something that's not a vector quantity. Mass, for example, okay? This is a 1 kilogram mass. It wouldn't make any sense to say, oh, this is a 1 kilogram mass north, okay? It doesn't. It's just mass. Boom, there it is, okay? So, and here's the subtle distinction, but it's important. If Abby just says, I walked 3 meters, okay, and all she gives me is a number, that's what we call a scalar quantity, okay? Mass is a scalar quantity, 1 kilogram, okay? If Courtney just says, I walked 3 meters, all that is a number, okay? That's a distance, okay? I don't have a direction with it. So if Courtney says, I walked 3 meters away from Abby, there's a whole bunch of different ways that she could walk 3 meters away from Abby. Now, if she says, I walked 3 meters north, that then becomes a vector quantity. Because not only did I know how far she walked, I know in which direction that she walked. Okay? Look at your cars. What indicates how fast you're going on your cars? A speedometer. Now, does that tell you which direction that you're going? No. Okay? That's what we call it, a speedometer, because it only tells you how fast you're going. You're going 40 miles per hour. You're going 50 miles an hour, or whatever it is. Okay? If it was actually telling you how fast you were going and in which direction you were going, it would be awkward, because then we'd have to call it like a velocipedometer, which sounds like some weird dinosaur, okay, that ran really fast. Oh, attacked by the velocipedometers, okay? But, sounds weird. So, huh?
Clever girl.
What?
Jurassic Park.
Oh, Jurassic Park. I saw that once. It was kind of a weird movie. It freaked me out. Okay, anyway. So, if all you have is a number, like when you look at your speedometer on your car. So here's like the test. If Paige took a selfie, okay, while she's driving, which is bad, okay, and in the background there was the speedometer, okay, and it was just showing 50, right? Stay with me here, okay? It's a story. I'm not recommending that you do this. All right?
The speedometer's behind you when you're driving. But anyway,
You're doing this.
okay, well, yeah, driving like that is not a good idea.
I know there's any number of reasons why this is a bad idea. But you're missing the point, okay? It's my story. You're missing the point, okay? If all I saw was that it was 50, all I would know is how fast she was going. I would not know a direction. Now, but let's say that her speedometer also has like a little compass indicator. And that compass indicator was saying south, okay? So if I saw that she was going 50 miles per hour, and the compass said that she was going south, now that indicates her velocity, because I know the magnitude, the number, And then I also know the direction that she was going south. Makes sense. You see, so you see the difference. So if it's just a number, it's a magnitude, it's a scalar quantity. If it's a number with a direction, then it becomes a vector quantity. Okay? Good so far. Perfect. Now, could you make the argument that Courtney's velocity is not zero? That she's actually traveling faster than the speed of sound right now?
If you use a different reference.
Change the reference point. To what?
The sun.
The sun, the universe. I don't know.
Well, we went a bit big with the universe. Okay? Now, let's say that you're outside the Earth and you can look down and you can see, oh, here's Courtney. Okay? And you're going to pick a reference point and say, okay, that some point, because this rock that we're on is spinning, okay, you would pick a point and say, okay, at some point later on, Courtney's position has changed. Now, what we've done is that we've shifted our frame of reference. If we change our frame of reference to the entire Earth, she is now traveling at about 430 meters per second. So we went from Courtney being at rest to traveling faster than the speed of sound because of the fact that we have changed our reference point. Now, in both situations, we're right, but we're all moving like 430 meters per second, right? You don't get this sensation because everybody else is, and everything is moving with you. Now, Courtney's and all of us are on this big rock that's orbiting this star that happens to be in our neighborhood, which is a good thing, right? And it's keeping us in this gravitational field and we're moving in this nice circle. So if you change the perspective to our solar system, then you would say, oh, Courtney has a velocity because she's on this rock that's orbiting this star. Okay? Now that's basically all we are. We're just on a big rock that has a lot of nice water on it. Okay? You can change the perspective even more. Our star is part of a Milky Way galaxy, and this Milky Way galaxy is a spider-arm galaxy that's moving around in this big, vast circle. So if you change the perspective to the Milky Way galaxy, Courtney and all of us are on this big cosmic, carousel ride around the center of the Milky Way galaxy. Now, if you really want to get really cosmic, you look at the entire universe like Captain America threw out here, and just want to get Captain America shirt, that's the reference. So, our Milky Way galaxy, like all galaxies in the universe, the galaxy itself is traveling through space. Okay? So, you can go from saying Courtney is at rest, sitting beside Abby, okay, to she's on this great journey through interstellar space as she's being drugged along as part of this Milky Way galaxy. So you can completely change that value based upon what you're going to set as your frame of reference. Okay? Now, let's say that Courtney's flying. Okay? All right? And Courtney wants to stand up and stretch her legs. So if this plane is, okay, flying, and here's Courtney, okay? And Courtney's walking towards the front of the plane, right? And the plane itself, say, is going 300 miles per hour. Okay? Now, if Courtney's walking towards the front of the plane, Courtney at this point might be going like 302 miles per hour because she's walking toward the front of a plane that's traveling at 300 miles per hour. If she's walking towards the back of the plane, her velocity is going to be a little bit less than 300 miles per hour. So it's very possible, if you've ever flown and walked in a plane, it's like, wow, I'm traveling at 400 miles per hour. Woo! Okay, don't say that on the plane. People kind of think you're weird. Okay, just if you do the woo sound. Okay, it's like wow. And then the stewardess asking for a different, seat. But if you look at where you are, okay, in terms of what your velocity is, even if you're in your car, okay, how fast are you going? 20 miles per hour, whatever it is. But if you walk, and not recommended, within your car, you can be going faster than 20 miles per hour. Again, maybe if you have a van, I don't know. So, here's my point. When you look at how you're defining a system, you have to talk about where you are. Now, let's say that Abby is on a train. Okay? Now, the train is kind of unique in the, I completely screwed this up. Okay, there's Abby. Okay? And the train is unique because Abby cannot see out of the train, okay, but you can see in. So Abby's got this big window here that we can look in and see Abby, but Abby can't see us on the outside. Now, Abby's going along at this train at a constant speed, okay, in a straight line. Constant speed, straight line. And let's say 40 miles per hour, okay? So this train is going in this direction in a straight line at 40 miles per hour. Abby happens to have 1 kilogram mass. Why, we don't know, but she does. Okay? Now, Abby, visualize this. Visualize this. Okay? You are inside this train, going in a straight line at 40 miles per hour, and you decide to throw the 1 kilogram mass up in the air. Where would it land? You throw it straight up in the air. Where would it land? Behind you? It's going to do one or two things. It's going to land back in your hand, or it's going to land behind you. It's going to land straight back in your hand, right? Okay, because it's going forward at the same time you are, right? Now, obviously, if you threw it like this, okay, yeah, okay. But assuming that you throw it straight up in the air, right, it's going to land right back here. True?
True.
How would you describe the motion? Straight up and straight down? Yes. Inside the car, Abby would say that that mass went straight up and came straight back down. Okay? Right? Now, Courtney is standing here. Okay? Right? And she's watching this train go by with Abby in it. And she sees Abby throw the 1 kilogram mass up in the air. Now, Abby says the mass goes straight up and it comes straight back down. Okay? Courtney, how would you describe the motion of the mass? Would you say that it goes straight up and comes straight back down?
Yes.
Yes? Read?
You just threw it a very long ways very easily. It goes up, but it goes forward too.
Yeah.
So it would go like in a rectangle?
Pretty much.
It would go up, over, hover, and then fall down.
Triangle.
Triangle.
Up and then back down because of the way the car is moving.
Upside down parabola.
Okay, let's mediate the two between a triangle and a rectangle.
Circle.
How about a parabolic curve?
That's the
Oh, I
word.
like that. Yeah. Okay. So
Exactly what I was thinking.
how about this? Okay. Kind of a democratic, rainbow thing. Okay. So it would go up and come back down. We're going to mediate this. Now, why are both of you right? What do you have in common, whether it's a rectangle or a triangle or a parabola? Why are both of you saying it's going to go forward? Why?
Because the train is going forward.
Bingo. Okay? So the train is going to impart a forward momentum to the mass just like it does to Abby. So if you're on the outside, you're going to see this thing travel in a parabolic path. Abby on the inside would say, no, it just goes straight up and comes straight back down. Who's right? Both of you are right. But it's a matter of your frame of reference. Okay? Abby's frame of reference is inside the train. Okay? So it's going to go up relative to a certain point and come back down relative to a certain point. You guys are seeing this thing moving. Okay? You're seeing it moving, so you're seeing it moving forward relative to some fixed point on the train platform. Both of you are right. Completely valid explanations. Now, this is where you have to, and don't think about this too much. But here's the question. If I drop this, which direction would you say it falls? Do not make this difficult. Downward, right? Within this frame of reference, this thing falls down. Now, if you look at the Earth, and here we are in Mays or Pretty Prairie, Kansas, okay? And if you're on the outside looking in, when someone drops this mass, obviously not to scale, but when you drop it, well, how would you say that it's going to, if you're on the outside watching this thing fall, which direction would you say it falls? Or inward, towards the center of the Earth, right? And almost sideways. Okay? Now, here's where this gets weird. If you're on the South Pole and you drop something, which direction does it fall? It actually falls upward. But it's still going to be falling towards the center of the Earth. Only at the North Pole, technically, and really not even the North Pole because we're on a tilted axis, you'd have to be at a point up here for this thing to classically what you call down. If you're here and you drop something, it's falling sideways. If you're on the bottom of the Earth, it falls up. So which direction it's going to fall is going to depend upon how you define that frame of reference. Cindy, you're shaking your head like, oh, I can't deal with this. Okay. All right. I'm done. We'll continue this tomorrow.
There is no camera off. Oh yeah.